Which of the following statements accurately describe the Gaussian random projection technique? A. It projects data points onto a lower dimensional space by randomly generating a matrix with normally distributed values. B. It preserves the pairwise distances between data points in the original space. C. It is primarily used for noise reduction in high-dimensional data sets. D. It is suitable for both linear and nonlinear data structures. E. All of the above. Font style quad font size 16 psquote. It projects data points onto a lower dimensional space by randomly generating a matrix with normally distributed values. Font. This statement is correct. Gaussian random projection uses a random matrix with normally distributed values to project data points onto a lower dimensional space. This effectively reduces the dimensionality of the data. Dimensionality reduction. Font style quad font size 16 psquote. It preserves the pairwise distances between data points in the original space. Font. This statement is partially correct. While Gaussian random projection doesn't perfectly preserve distances, it offers an approximation that is beneficial for many applications. The Johnson-Linden-Strauss lemma states that random projections can approximately maintain pairwise distances with a high probability. This approximation is crucial for tasks like nearest neighbor search and clustering, where the relative distances between data points are essential. Johnson-Linden-Strauss lemma. Font style quad font size 16 psquote c. It is primarily used for noise reduction in high-dimensional datasets. Font. This statement is correct. Gaussian random projection is widely used to reduce noise in high-dimensional datasets. By projecting data onto a lower dimensional space, it can effectively filter out irrelevant variations that could obscure meaningful patterns. Noise reduction. Font style quad font size 16 psquote d. It is suitable for both linear and nonlinear data structures. Font. This statement is correct. Gaussian random projection works well with linear data sets. It can also be applied to nonlinear data sets, but some nonlinear relationships may be lost in the process. The effectiveness of Gaussian random projection on nonlinear data depends on the complexity of the data structure. Linear and nonlinear data structures. Font style quad font size 16 psquote e. All of the above. Font. This statement is correct. Given that statements A, B, C, and D are all true, statement E, all of the above, is also true. Gaussian random projection is a versatile technique with numerous applications. Gaussian random projection. E. From sklearn. Random projection import Gaussian random projection. From sklearn. Datasets import make blobs. X, Y make blobs and samples 100, and features 5, centers 3, random state 0. Transformed Gaussian random projection components 2. Fit transform X. Prints transformed. 1. High-dimensional data analysis. Gaussian random projection excels in handling large datasets with numerous features, effectively reducing dimensionality while preserving important information. High-dimensional data analysis. Imagine analyzing customer data with hundreds of attributes like demographics, purchase history, website interactions, etc. Gaussian random projection can reduce the dimensions to a manageable set, enabling efficient analysis while retaining key patterns. 2. Image recognition. It can be employed for image dimensionality reduction, enabling more efficient processing and classification. Image recognition. In image recognition systems, images often have a high number of pixels. Gaussian random projection can reduce the dimensionality of image data without losing important features like edges, textures, and shapes, thus speeding up image classification algorithms. 3. Text mining. Gaussian random projection can be used for dimensionality reduction of textual data, facilitating faster topic modeling and sentiment analysis. Text mining. Analyzing large volumes of text data, like customer reviews or social media posts, involves representing each document as a vector of words. Gaussian random projection can reduce the dimensionality of these vectors, allowing for faster processing of text data, leading to more efficient topic modeling and sentiment analysis. 4. Anomaly detection. By reducing the dimensionality of the data, it can help in identifying unusual patterns or outliers. Anomaly detection. Detecting fraudulent transactions in a financial system often involves analyzing high-dimensional data like transaction amounts, locations, times, and user profiles. Gaussian random projection can reduce the dimensionality of this data, making it easier to identify transactions that deviate significantly from normal patterns. 5. Collaborative filtering. In recommender systems, it can be used for dimensionality reduction, which aids in finding similar items or users. Collaborative filtering. In a movie recommender system, users and movies are often represented as vectors in a high-dimensional space. Gaussian random projection can reduce the dimensionality of these vectors, making it easier to identify users with similar tastes or movies with similar themes, thus improving the accuracy of recommendation algorithms. Style quad font size 14 psquot dimensionality reduction. The process of reducing the number of features or dimensions in a dataset while preserving the essential information. Dimensionality reduction aims to simplify complex datasets by reducing the number of variables while preserving the most critical information. This helps with visualization, computation efficiency, and reducing the impact of the curse of dimensionality, a phenomenon where performance deteriorates in high-dimensional spaces. Style quad font size 14 psquot random projection slowed techniques that use random matrices to project data points onto a lower dimensional space. They aim to preserve the essential structure of the data. Random projections utilize random matrices to map high-dimensional data to a lower dimensional space. These techniques are based on the idea that randomly generated matrices can effectively preserve the distance relationships between data points, making them useful for various tasks, including dimensionality reduction, similarity search, and classification. Style quad font size 14 psquot Johnson Linden Strauss Lemel a theoretical result that provides a foundation for random projection techniques. It states that random projections can approximately preserve pairwise distances. The Johnson-Linden-Strauss lemma is a fundamental theorem that supports the use of random projections for dimensionality reduction. It states that with a high probability, a random projection onto a lower dimensional space can preserve the pairwise distances between data points within a small distortion factor. This guarantees that the essential structure of the data is maintained, making it suitable for various data mining and machine learning applications. Style quad font size 14 psquot normal distribution. A common probability distribution characterized by its bell-shaped curve. The Gaussian random projection technique uses random values drawn from a normal distribution. The normal distribution, often called the Gaussian distribution, is a symmetrical probability distribution with a bell-shaped curve. Its importance stems from the fact that many natural phenomena, such as human height, blood pressure, and measurement errors, tend to follow a normal distribution. In Gaussian random projection, random values are drawn from a normal distribution to construct the projection matrix, which effectively maps data points to a lower dimensional space. Style quad font size 14 noise reduction. The process of removing or minimizing unwanted noise from data, which can improve the accuracy and interpretability of analysis. Noise reduction is an essential step in data analysis, aimed at eliminating or minimizing irrelevant variations or errors in data. These variations, known as noise, can hinder the accuracy and clarity of analysis, making it difficult to identify meaningful patterns and trends. Noise reduction techniques aim to enhance the signal-to-noise ratio, improving the quality and interpretability of data. Which of the following is a valid use case for sparse random projection in sklearn? A dimensionality reduction for images in a face recognition system. B. Feature extraction for text classification. C. Reducing the number of features in a dataset with many sparse features. D. All of the above. A dimensionality reduction for images in a face recognition system. Correct. Images, particularly those with high resolution, can be represented as matrices with many zeros. Sparse random projection is ideal for reducing the dimensionality of such images while preserving key information. True. B. Feature extraction for text classification. Correct. Text data often has a high number of unique words, but most are infrequent. This results in sparse feature vectors. Sparse random projection can effectively reduce the dimensionality of text data while retaining important features for classification. True. C. Reducing the number of features in a dataset with many sparse features. Correct. Sparse random projection is designed to handle datasets with sparse features, like those found in genomics, text analysis, and many other fields. It helps reduce computational complexity and improve model performance by efficiently projecting the data onto a lower dimensional space. True. D. All of the above. Correct. All of the above options are valid use cases for sparse random projection, as it effectively leverages sparsity for dimensionality reduction and feature extraction across different data types. True. D. All of the above. Dimensionality reduction. Transforming high-dimensional data into a lower dimensional space while preserving key information. Consider a dataset with 100 features describing customer demographics. Using PCA, we can reduce these features to 10 principal components, capturing most of the variance in the original data. This allows for more efficient model training and visualization. Sparse data. Data with a high percentage of zero values. A document term matrix in text processing, where most words are not present in a given document, resulting in many zero entries. This sparsity is leveraged by techniques like sparse random projection. Feature extraction. Transforming raw data into a set of features that are more informative for a machine learning model. Converting raw image pixels into features like edges, textures, and shapes for object recognition. This process extracts relevant information from the data for better prediction. Scikit-learn sklearn. A popular Python library for machine learning, offering a wide range of algorithms and tools for dimensionality reduction, classification, regression, and more. Using sklearn.decomposition.pca for dimensionality reduction, sklearn.linearmodel.logistic regression for classification, and sklearn.ensemble.random forest regressor for regression. Sparse random projection. Python. From sklearn.random projection import sparse random projection. SRP sparse random projection components 50, density auto. X reduced SRP.fit transform X. This code uses sparse random projection to reduce the dimensionality of a dataset X to 50 features, leveraging its sparsity. What is the function sklearn.randomprojection.Johnsonlindensstraßmindem used for? A. It estimates the minimum number of dimensions required for a random projection to preserve pairwise distances with a given accuracy. B. It calculates the optimal number of features to keep after applying PCA. C. It performs a random projection to reduce the dimensionality of data. D. All the above. It estimates the minimum number of dimensions required for a random projection to preserve pairwise distances with a given accuracy. This statement is correct. The Johnson-Lindens-Straßmindem function utilizes the Johnson-Lindens-Strass lemma to determine the minimum number of dimensions required for a random projection while maintaining the pairwise distances with a specific level of accuracy. It uses the desired accuracy epsilon and the number of data points n as input parameters. True. Answerld font color quote 0000 F quote correct Answerld font D. All the above font color quote 0000 F quote explanation font sklearn.random projection.Johnson-Lindens-Straßmindem estimates the minimum number of dimensions needed for a random projection to preserve pairwise distances with a desired accuracy. It leverages the Johnson-Lindens-Strass lemma to achieve this goal. X20. It calculates the optimal number of features to keep after applying PCA. This statement is incorrect. While both PCA and random projection aim to reduce dimensionality, Johnson-Lindens-Straßmindem is specifically designed for random projections, not for determining the optimal number of features after applying PCA. PCA uses a different approach based on eigenvector decomposition. False. Answerld font color quote 0000 F quote correct Answerld font D. All the above font color quote 0000 F quote explanation font sklearn.random projection.Johnson-Lindens-Straßmindem estimates the minimum number of dimensions needed for a random projection to preserve pairwise distances with a desired accuracy. It leverages the Johnson-Lindens-Strass lemma to achieve this goal. X20. It performs a random projection to reduce the dimensionality of data. This statement is incorrect. The Johnson-Lindens-Straßmindem function itself does not perform the random projection. Instead, it calculates the minimum number of dimensions needed for a successful random projection to be applied. It's a helper function for dimension estimation. False. Answerld font color quote 0000 F quote correct Answerld font D. All the above font color quote 0000 F quote explanation font sklearn.random projection.Johnson-Lindens-Straßmindem estimates the minimum number of dimensions needed for a random projection to preserve pairwise distances with a desired accuracy. It leverages the Johnson-Linden-Strauss lemma to achieve this goal. X20. All the above. This statement is correct. All the previous statements are accurate descriptions of what the Johnson-Linden-Strauss Mindem function accomplishes. True. Answered font color quote 0000 F quote correct answered font D. All the above font color quote 0000 F quote explanation font sklearn. Random projection. Johnson-Linden-Strauss Mindem estimates the minimum number of dimensions needed for a random projection to preserve pairwise distances with a desired accuracy. It leverages the Johnson-Linden-Strauss lemma to achieve this goal. X20. D. All the above. Dimensionality reduction. One-dimensionality reduction, the process of reducing the number of random variables or features in a dataset. Consider a dataset with 1000 features describing images. By applying dimensionality reduction techniques like PCA or random projection, we can reduce the number of features to 100, for example, while preserving the essential information for tasks like image classification. This can significantly reduce the computational cost and storage requirements. Random projection. Random projection, a technique that projects high-dimensional data onto a lower-dimensional space by multiplying the data with a random matrix. Imagine projecting a 3D point x, y, z onto a 2D plane by multiplying it with a random 2x3 matrix. This effectively reduces the dimensionality of the point while preserving some aspects of the original relationships between points. Johnson-Linden-Strauss lemma. Johnson-Linden-Strauss lemma, a mathematical theorem stating that a set of points in a high-dimensional space can be embedded into a much lower-dimensional space while preserving the distances between the points with a high probability. X20. Suppose you have a set of 100 points in a 1000-dimensional space. The Johnson-Linden-Strauss lemma guarantees that you can project these points into a much lower dimensional space, example 50 dimensions, using random projection, and the distances between the points will be preserved with high probability. This allows efficient computations and data storage.